Hello everyone. In today's class on advanced characterization techniques, we are going to study a few things about properties of neutron radiation and neutron sources. Up till now, in this course, or rather this module of the course, we have been dealing with mostly X-ray diffraction and electron diffraction. But now we are going to look at a different class of radiation, that is neutron diffraction. So all of us are aware what exactly are neutrons. So we know that neutrons are essentially subatomic particles which are there sitting in the nucleus along with the protons. These particles are characterized with no charge and have mass which is equal to 1.675 into 10 to the power minus 27 kg. We are also aware that this mass of neutron is slightly higher than that of protons. Now, in addition to the mass, neutrons are also characterized with a spin of half and nuclear magnetic dipole moment of 1.913 times that of a nuclear magneton, which is approximately equal to about 5.05 into 10 power minus 27 joule per Tesla. So, having said that, we know that neutron as such is a very different subatomic particle when compared to proton and an electron. Now, with the exception of hydrogen 1, all atoms consist of neutrons and protons. In fact, the neutrons bind the protons together in the nucleus, because the protons with all their positive charges have a tendency of repelling each other. The neutrons actually act as glue that holds all the protons together in the nucleus. Having said that, we are also aware that if in the same for the same atom we can have a situation wherein the number of neutrons are different in the nucleus, and such kind of atoms are actually known as isotopes. One of the classical example of an isotope is the carbon 12 and carbon 14 isotope, wherein we know that the carbon 12 isotope is actually characterized by 6 protons and 6 neutrons, while the carbon 14 isotope that we are having has 6 protons, but in this case we have 8 neutrons. Okay. So, moving ahead, we also know that the bound neutrons in the nucleus are absolutely stable. However, the unbound neutrons, which are just not associated with the nucleus, are highly unstable. Well, what exactly I mean when I say that they are unstable? Well, the neutrons undergo what is known as beta decay. What happens in a beta decay is that a neutron gets transformed into a proton, a electron and a electron antineutrino. Let us not get into nuclear physics, but for the time being, and assume or rather understand that it is not possible to have unbound neutrons, okay, as a source for carrying out neutron diffraction or neutron scattering experiments. Therefore, another important point that needs to be noted, that all this dissociation or decay mechanism that I told ensures that the lifetime of the neutrons is only about 15 minutes, and therefore it is necessary to produce neutrons as and when required. Coming back, how to produce neutrons? Well, we can always produce them using nuclear fission as well as nuclear fusion. I am not going to talk much about fission and fusion, but let us talk about neutrons as a particle. We know that neutrons are subatomic particles, and quantum mechanically they show wave particle behavior. So, for a neutron traveling at a particular velocity, we can always assign a particular wavelength and treat it as a wave with that particular wavelength according to the de Broglie wavelength criteria. Now, the beauty about neutrons as a source for carrying out diffraction or scattering is essentially that the velocity at which the neutrons travel when combined with their mass essentially ensures that the kind of wavelength that we are going to get is of the order of angstroms, which falls in the range of that of X-rays, and this is what ensures that we can use neutrons for carrying out diffraction experiments, where also the interatomic or rather interplanar distances are of the order of few angstroms. But when compared to X-rays, neutrons offer much better penetration depth, and that is essentially because neutrons essentially interact with the nucleus of the atom. Now, if you look and consider an atom, the nucleus occupies a much smaller region compared to the entire size of the atom, because most of the region is occupied by the electron cloud. Having said that, this ensures that the neutrons have a much better penetration depth compared to X-rays, and it can be as high as a few millimeter in materials with high density. As I had already mentioned, this is essentially due to the fact that neutrons see, or rather feel, only the nucleus and not the electron cloud. So, they travel essentially through a very open structure compared to X-rays or electron that see, or rather interact with the electron cloud. The same philosophy or the same concept is shown over here in this figure. So, if you look at a free surface over here and consider it comprises of all these atoms with the dark spot at the center being the nucleus and the electron cloud surrounding it, you see that the neutrons actually interact with the nucleus, right, and it can undergo diffraction or scattering, while the X-rays interact with the outer electrons and it undergoes X-ray scattering or diffraction. Therefore, we can assume that the probability of X-rays interacting with an atom is much higher than that of a neutron, and therefore, the penetration depth of neutrons is much higher than that of X-rays. Having said that, neutrons also have a tendency to interact with the dipole. Mind you, we had talked that neutrons have a particular spin and a magnetic dipole moment associated with it, and therefore, the neutrons can interact with free electrons that also have a dipole moment, and this dipole-dipole interaction can give us information about magnetic scattering or diffraction. I will like to bring to your notice that neutron diffraction is probably one of the most sophisticated technique that can give us some information about the magnetic structure of the material. Having said that, let us try to understand how exactly diffraction takes place when neutrons are used as a source. Well, the concept is exactly similar to that of X-rays. Only thing is, instead of X-rays getting bounced off from the outer part of the atom, we have neutrons which get bounced off, or rather reflected from the nucleus of the atom. Therefore, we get an interference pattern very similar to that of X-rays or electrons. The diffraction theory for X-rays and electrons can be easily extended to that of neutrons, and therefore, the scattering and diffraction principles that we employ for X-rays and electrons can be borrowed one-to-one for neutrons also. This actually ensures that Bragg's law is valid for neutron diffraction, and that we can carry out all the X-ray diffraction and scattering techniques that we talked about using neutrons. However, as I had already mentioned, one of the best part or rather the best kind of property of neutrons that is on offer, which is not there for electrons and X-rays, is that they can give us information about the magnetic structure. Now, this information is not given either by X-rays or electrons, but neutrons can offer us information regarding the magnetic structure of the material under consideration, in addition to the crystal structure. Okay, so now when it comes to generation of neutrons, so we had talked how we generate X-rays, right, different ways of generating X-rays. Similarly, neutrons also can be generated in different ways. Essentially, we have to draw off the neutrons from the nucleus of the atom, and this can be done using a fission reactor. In a fission reactor, we use a neutron source like radioisotope californium-252. Now, this releases neutrons which are bombarded on a U-235 nuclei. This leads to fission of the uranium nuclei and release of neutrons. Now, with the use of proper moderator, we can control the number of neutrons that are released, and this can act as a continuous source of neutrons, right. Another important way of producing neutrons is using what is known as a spallation source, in which case we use synchrotron to accelerate protons to very high energy of the order of giga electron volt range, and focus this beam on depleted uranium target, or these days the most favored target is tantalum, which ensures that neutrons actually fall off, or rather spall off from this material, that is from uranium target or tantalum target, giving a pulsed source of neutrons. I would like to mention that a fission reactor can be used for producing nuclear fuel, and therefore, in most countries it is generally not used for academic activities. However, a spallation source is more appropriate and most of the time is used regularly. However, one of the biggest problem with spallation source is that it produces a lot of radioactive waste that comes from the target material. So, once the accelerated protons hit the uranium or tantalum target and gives out neutrons, the leftover material is highly radioactive. So, this is one of the drawbacks of the spallation source. But having said that, depending on the kind of energy that we have, we can have neutrons into different neutrons can be classified into different regimes. So, if you look at hot neutrons are moderated at 2000 degrees centigrade. They have energy range of about 0.1 to 0.5 electron volt, wavelength of about 0.3 to 1 angstrom, and travel at a velocity of 10,000 meter per second. There are thermal neutrons which are moderated at about 40 degrees centigrade. They have energy range of the order of 0.01 to 0.1 electron volt, wavelength of the order of 1 to 4 angstrom, and travel at a velocity of 2000 meter per second. Mind you, I hope you have noticed that the thermal neutrons probably are the most important neutrons, because look at the wavelength. Their wavelength is of the order of X-rays that we use in a laboratory. Having said that, look at the energy level that we are having. The energy level is of the order of 1/10 to 1/100th of an electron volt, that is in the range of a few milli electron volt. In order to produce the same wavelength, if you remember, we are using a voltage of the order of kilo electron volt when it came to X-rays. So, I hope this point is very well taken, that we can get the same wavelength of neutrons at a much lower energy level. Now, there are also what are known as cold neutrons. So, these cold neutrons are actually moderated at 2000 degrees centigrade, and they have energy which is lower than 0.01 electron volt and a wavelength of the order of 0 to 40 angstrom, and travel at a speed of 200 meter per second. So, most of the cases that we will talk mostly will focus, since we are keeping X-rays and electrons as our focus, I will talk mostly about thermal neutrons which form in the same range as that of our X-rays. So, from all these sources, what is the kind of spectrum, right? Like, what is the kind of neutrons that we get? Do we get neutrons of same frequency and energy, or a different energy? Well, like X-rays also, we get, we have a continuous spectrum and we have a characteristic peak. Not here for neutron. In case of neutrons, if you look at the intensity versus wavelength plot, we see that the neutrons follow a Maxwell distribution, which has been depicted over here. Most of the times, we do not need a wide range of energy distribution, and therefore, we use monochromators to choose only a wavelength of our interest and use it for further use. Now, one of the most important part, which we had talked about during X-ray as well as electron diffraction, is actually the scattering cross section. The scattering cross section essentially defines the probability of scattering event between neutrons and nucleus. For a plane wave Eikz, a scattered wave which is f of theta and phi and is multiplied with e raised to the power I k r by r. Now, this gives us the scattering probability, right. If you remember, this is exactly similar to what we had for X-rays, and this term f of theta phi is nothing but equivalent to the structure factor that we had used in case of X-rays. So, the differential cross section, if you are about to calculate, is d sigma by d omega, which is nothing but proportional to square of the structure factor. Now, this is nothing but the intensity that we get. You remember in X-rays we had also talked about this is just a change in terminology, but in case of X-rays we had this intensity proportional to the f square. Now, if you go for integral cross section, which is nothing but you integrate this differential cross section. So, which is sigma is equal to integral d sigma d omega by d omega. This d omega is the solid angle. We will talk about it in a later slide, but this essentially gives us a measure of effective surface area seen by impinging particles. So, the affected area presented by nucleus to an incident neutron is actually represented in terms of a bar, which is nothing but a unit of area, and 1 bar is equal to 10 into minus 27 meter square. Having said that, another important point that needs to be noted is that once the neutrons are travelling and they interact with matter, they are going to get attenuated. That means their velocity is going to change, and therefore, the attenuation is given as exponential minus n sigma t, where n is the number of atoms per unit volume and t is the thickness. So, the cross sectional is proportional to the square of structure factor. Now, this is very important in determining the intensity of the diffracted beam. Coming back again, the reason we are talking so much about neutron cross section is actually because of the wave nature and particle nature, right. So, here neutrons can also be considered as particle nature, while in case of X-rays we just ensured that intensity is proportional to the structure, the square of the structure factor. Having said that, this will be more clear with this drawing over here, wherein you see we have incident neutrons which are coming over here, and this is the target. We see that how the neutrons get diffracted in a particular direction. So, if at all we have a neutron flux of phi, which is nothing but the number of neutron per unit area per time, and the sigma is the total number of neutrons scattered per second for a incident flux of phi. So, our d sigma by d omega, where d omega is the solid angle that is covering, is actually the number of neutrons scattered per second into d omega, right, and this is for phi d phi, isn't it, and therefore, our d sigma by d phi is nothing but the number of neutrons scattered per second into d omega in an energy range of about dE, right. So, we see that we have incident and what is the probability of neutrons getting diffracted. So, this is nothing but the fraction of neutrons that are getting diffracted in a particular direction omega. So, this is nothing but your neutron cross section, and this is absolutely proportional, or rather directly proportional to the square of the structure factor. So, let us talk, as I had already mentioned, that the neutrons actually interact with the nucleus of the atom and not with the electron cloud. So, if you look at the nucleus, you know that there is a nuclear force associated with the nucleus. Now, the range of the nuclear force is very small and of the order of few femtometers. We are also aware that the kind of wavelength that we are using for neutrons is of the order of few angstroms. Therefore, we have a situation where the wavelength of the neutrons is much larger than the range of the nuclear force. Therefore, the energy of the neutron is much lower than the energy of the nucleus, and this ensures that there is no energy transfer between neutron and nucleus. This actually ensures that once you have a neutron interacting with a nucleus, it does not lose its energy, and therefore, all the scattering and diffraction phenomena that are occurring are essentially elastic. the wavelength, as I had already mentioned, is actually decided by the velocity, because lambda is equal to h divided by the momentum, which is nothing but mv. So, the velocity of the neutrons does not change. However, their angle, the d omega part, right, in the last slide we had talked about, may change. So, the scattering is far from nuclear resonance, and there is no absorption of neutrons in during interaction of a neutron with the nucleus of an atom. A schematic diagram of the same is shown over here, where we have this incident beam of planar neutron beam, right, and here we see that the number of neutrons per area ds per second after scattering is VDS phi scattering square. This is again your wave square, the wave equation which is squared, that gives you the intensity. ds is the area and v is the velocity. So, at the end of the day we end up getting equal to VA square d omega, where d omega is the angle. It has not been shown over here, but see, it is a solid angle, right, and A, you know that the scattered circular wave has the equation of minus A by r e raised to the power I k r, right. So, now the number of incident neutrons per unit area ds, which is your phi, right, is nothing but V xi incident square, which is nothing but equal to V, and the cross section d sigma by d omega is equal to A square, right. So, depending on the scattered circular wave amplitude, okay, we are going to get the d sigma by d omega, and as you can see, the total scattered neutron is nothing but in a solid angle, right. Once you integrate, you get 4 pi A square, right. This is where this term is very similar to that of the surface area of the sphere. Okay, so we are considering all spherical waves. So, the point is, I would like to repeat again that the neutron cross section is actually proportional to the square of the amplitude, right, like this is what we got even for X-rays. Only thing is, we are trying to derive it in a slightly different way, because here we are going, instead of having a wave approximation, we are trying to explain the same thing using a particle approximation. Having said that, at the end of the day we end up getting the same solution, right. So, in X-rays, or for that matter in electrons, right, like in electrons we talked about coherent scattering and incoherent scattering. So, the actual scattering length, right, for neutrons with the nucleus is actually given, say, by AI, which is nothing but A plus delta AI. Now, the delta AI essentially indicates a random component, right. So, the random component of scattering vector contributes to incoherent scattering. So, the contribution of A, this summation of A, or rather bracket of A, actually corresponds to elastic, while this delta AI corresponds to inelastic scattering. Now, the information about collective motion and relative position of the nuclei is given by coherent scattering. So, this is very similar to what we are having, right, like where your atoms are sitting, that means where your nuclei are sitting, and where your neutrons are getting interacting with the nucleus and getting scattered. So, this is because of coherent scattering. However, we also know, we have seen this Debye-Waller like term, that you know, at only at 0 Kelvin all the atoms are sitting at their own place in the unit cell. In fact, at any temperature other than 0, they are actually vibrating, right. So, we actually get a motion of individual nucleus, and that actually leads to incoherent scattering. Now, this contributes actually to this delta AI term. Now, this term is slightly different than the Debye-Waller term, because that is taken care of, but any small perturbation in the nucleus is actually captured using incoherent scattering. To just give you an example, I will mention that you have cross sections associated with both coherent as well as incoherent scattering. Having said that, a classical example is that of a hydrogen, which has a very low coherent scattering cross section, and therefore cannot be detected using normal neutron coherent scattering neutron experiments. However, it has very nice or rather very high incoherent scattering cross section. Therefore, if you want to study diffraction experiments, mostly hydrogen is replaced with deuterium, which has a very good rather a very high elastic or rather coherent scattering cross section, but has very poor incoherent scattering cross section. So, this way you can see that we can use different kind of scattering events, namely coherent and incoherent, to detect the presence of a particular element, or rather more to be more precise, a particular isotope in neutron scattering or diffraction. Mind you, if you want to study diffraction, where we need to carry out which corresponds to coherent scattering, we have to use material, or like we will get better signal for deuterium. Therefore, people who work on ice, which is H2O, solid H2O, actually replace hydrogen with deuterium to carry out neutron diffraction studies to determine the crystallographic texture. While if you are more interested in studying the spectroscopic aspect of it, we can always use hydrogen. Having said that, another important aspect with neutron diffraction, if you remember, for X-ray diffraction, which X-ray diffraction does not have to offer, is the scattering cross section, right. So, if you remember, we had the scattering cross section, or rather the intensity was proportional to f square in case of X-rays, and f was nothing but it was your atomic number. So, it is not possible to differentiate between two elements which are very close to each other in the periodic table. However, look what happens when we look at neutron cross section, which is given over here in terms of scattering length. We see that two atoms, or like two elements which are very close to each other, have very different, right. You see aluminum and chlorine, they have quite a different scattering cross section. This essentially ensures that we can easily separate out these two elements which are very close in periodic table using neutron diffraction. At the same time, we also see that we get information about the magnetic cross section also. So, you see here we have nickel 62 here, and we have another nickel. So, the scattering cross section for nickel and the magnetic cross section, okay, they are two different. So, we can actually find out where our nickel atom is sitting and where the magnetic moment is sitting, right. Ditto for cobalt, and you see here for different isotopes of nickel, you see the huge amount of difference in the scattering cross section. Now, this information is offered only and only by neutron diffraction. The similar information is presented in a very nice way over here. So, we can see here the X-ray relative scattering length. We see hydrogen is small, carbon bigger as it moves as a function of Z. However, when we look at neutron, we see that there is no one-to-one correspondence between Z, that is atomic number, and the scattering length. Okay, and see we can easily separate out between adjoining elements. Taking forward our comparison between neutrons and X-rays, we have seen that neutrons actually behave like particle and wave, while X-rays are actually electromagnetic wave. Now, neutrons have a mass associated with it, while X-rays have no mass associated with them. Neutrons have a spin of half, while X-rays have a spin of 1. They have a magnetic dipole moment, while X-rays have no magnetic dipole moment. The neutrons actually interact with the nucleus, while the X-rays interact with the electron cloud. Now, neutrons are scattering power independent of 2 theta, which has been shown over here. So, you see what happens, the intensity versus sin theta, well, it is almost a straight line. Well, it is always a straight line because it is not dependent on the angle. While when we talk about X-rays, we know that this value decreases. Remember, we had seen this f versus sin theta value, how it was decreasing. It started from z and it was reducing continuously as a function of theta. Not so for neutrons. Now, neutrons with their kind of energy they have, and since they interact only with the neutrons, have very low absorption, while X-rays get absorbed a lot. But there is a problem. Since neutron interaction is weak, we need large amount of sample, while with X-rays we can live with small amount of sample. Now, in neutrons, the neighbors as well as isotopes can be easily discriminated, right? While for X-rays, the neighbors, isotopes, there is no way we can see isotopes. Neighbors, the discrimination is very, very difficult. The detection of light element is very difficult in X-rays, while it can be done on a routine basis in neutrons. One of the biggest USPs of neutrons is that it can be used to determine the magnetic structure, while no magnetic structure information is obtained from X-ray diffraction. As we had already seen that the neutron is a very weak source, or rather a very weak probe, but this is not a disadvantage, because a weaker probe ensures that the kind of interaction that we are seeing is not because of an artifact or any change in the state of the matter that we are studying. I would like to mention that the X-rays are intense source, and when I say intense, I am not really talking about synchrotron, but even a normal X-ray laboratory source is almost 1000 times brighter than a neutron source. Having said that, we should always remember that neutron sources are not available at every place, and in fact there are hardly a few places in the world, while X-ray sources and X-ray diffractometers are available at every university, and therefore can be used on a day-to-day basis. Just to show you but having said that, it's not like X-rays are good and neutrons are bad. In fact, these two techniques are completely complementary to each other, and this particular slide kind of encompasses the basic complementary nature of both the techniques. So, look at different elements. We have shown different elements over here, and see how the neutron cross section and the X-ray cross section varies. So, you see that materials with high X-ray cross section have low neutron cross section, right. Therefore, you can see that if there is a situation where we have material with high X-ray cross section and high neutron cross section at the same time, we can always use X-ray and neutron diffraction or scattering technique to complement and get complete information from the sample under investigation. Now, just to compile, what are the advantages of neutrons over X-rays? Well, both of them have comparable wavelength in the angstrom level. However, the energy of neutrons is much lower. The neutron lower energy, as I had already mentioned, ensures that there is no harm to the sample, there is no damage to the sample. The interaction of neutrons with the sample is more of what happens in a ping pong ball, right, like which gets thrashed from one place to the other, while in case of X-rays, the X-ray photon is like a cannonball which is going through the structure, right. Neutron diffraction therefore can predict where atoms are, that is the nuclei are, and what they do. This is something that X-rays cannot tell. X-rays just tell us where the atoms are, right, but they do not tell where the nuclei are, and therefore atomic structure and dynamics can be estimated directly, mind you, only using neutrons. The dynamics part come because neutron diffraction not only tells us where the atoms, or rather the nuclei are, but also what they are doing. Fine. So, this is one of the biggest advantage of neutron diffraction. We know that neutron scattering cross section varies randomly, right, like we had seen those curves that it is not dependent on Z. Now, this ensures that we can easily differentiate close elements in the periodic table. At the same time, we also have this ability to differentiate between isotopes, right, the different isotopes of the same element using neutrons. X-rays have no capability to differentiate between the isotopes. As we had seen, neutrons offer a very weak probe, and therefore it gives us a very better signal. Though the signal is very weak and it takes some time to collect and amplify the signal, the weak probe actually ensures that no damage is caused to the material under investigation. More importantly, no damage is caused to the structure of the material under consideration. We have seen that neutrons have higher penetration depth, and they are very useful for getting bulk properties. Many a times, if our grain size is very large, right, if the grain size is very large, X-rays cannot penetrate, and they cannot give us complete information about the kind of phases and, say for that matter, preferred orientation that is present in a material. This is where neutron diffraction becomes very important, and this is something that can be done only with neutron diffraction. So, whenever it comes to getting statistically relevant data for a normal neutron, for a normal diffraction data, we can always use neutron diffraction. The biggest advantage, and which I am reiterating again and again for neutrons, is that they give information about the magnetic structure. Neutrons are essentially neutral particles with spin of half and have a magnetic dipole that interacts with the magnetic dipole of outermost electrons in an atom. This ensures that we can determine not only the crystallographic as well as but also the magnetic crystal structure of the material under investigation. Now, this is one of the best advantage of neutron compared to that of X-rays. Now, talking about instrumentation. Now, this is some slide that we had already seen. We saw that this was for X-rays. So, we had a source, incident beam optics, a sample, a diffracted beam optics and a detector. We have something similar, not exactly the same, but something very similar for neutrons. We will try to see how actually we have instruments for carrying out neutron diffraction. So, let us start with the source. So, as we had seen earlier, like we have a reactor as a source for neutron diffraction, for producing neutrons. The reactor is a continuous source, and which is shown over here. So, you see intensity, you see there is a constant intensity, right. Peak intensity is limited by cooling capability in nuclear reactors. You see the intensity is quite low. However, if you have a spallation source, which we had talked about earlier, it is a pulse source. We see here, instead of having a continuous energy level, we do get pulses, right. This is as a function of time, and here the intensity of the pulses is much higher because of better cooling control. Okay. But having said that, we know that we do not get a continuous spectrum, but the intensity is nevertheless higher. Now, for the continuous spectrum, right, this is very similar to what we have for X-rays, and once we put a monochromator, we can use a normal diffractometer for continuous source and do the same kind of study that we did for X-ray diffraction. However, if you are using a pulse source, mind you, we have to use a time of flight measurement, wherein we measure the time taken by the neutrons to travel the same distance. Mind you, once the neutrons get scattered at different angles after interacting with the material, they are going to take different time to reach the detector, and this can be used to measure the diffraction, the scattering angle and intensity using time of flight measurement, right. In time of flight, we know that the velocity, or rather the mass of the neutrons is the same. Their velocity is also the same, but depending on the angle of scattering, they are going to take different times to reach the detector. So, this technique is actually known as time of flight technique. This technique is very fast, and however, we need very high flux for it. Now, this diffractometer data acquisition and analysis is very simple and very well suited for magnetic studies, and gives us a very good resolution at low angles. However, at high angles, we do not have any other choice but to go for time of flight measurements. So, just to talk about, we talked about the optics. So, let us talk about the optics. We have seen the source. Now, we have what are known as neutron guides. Now, what the neutrons guide do? Essentially, they reduce the beam delivery losses and ensure that the the neutrons are traveling in a particular direction, right. Then we also have what are known as neutron choppers. Now, these neutron choppers actually are rotating mechanical disks with openings that actually control the initial velocity of the neutrons. Remember that we have to, this initial velocity of the neutrons, when I say, actually ensures that you are getting neutrons in a particular energy range. That is what we are aiming at, right. So, this is what we want. Then all this neutron, that is incident, that interacts with the sample, and then we have a detector, which requires the time required for a neutron of a particular energy to reach the detector, right. The scattering angle is related to position of the neutron detector. Now, talking in details, we know that in X-ray optics also, to get a wavelength of a very radiation of particular wavelength, we used what are known as monochromators. For neutrons also, we use mosaic monochromators, which are nothing but asymmetrically cut single crystals. This ensures that neutrons with only a particular wavelength are able to pass through. Okay. Similarly, the neutron guides actually reflect the neutrons, right? They reflect the neutrons and thereby reduces the path that is available for the neutrons to travel. These comprises of glass plates with about 150 nanometer of nickel coating. So, the neutrons which are incident get reflected and are guided to a particular region. The chopper, as I had mentioned, comprises of rotating mechanical devices that block neutrons of various energy and allow only neutrons with very low bandwidth to pass, right. So, we had seen that there is a Maxwell distribution. Of the Maxwell distribution, we allow only a small part to pass using chopper. There are certain investigations wherein we need polarized neutrons, right, for doing magnetic study. So, in that case we use a flipper. Now, how does a flipper work? I will show you in the next slide, but keep in mind which is shown over here. So, you see here we have neutrons which are having both kinds of spin, right, plus half and minus half. Now, we have a substrate which is essentially silicon and a magnetic film coating on it, right. So, you can have iron or niobium, and we see that all the neutrons which are incident on it get polarized, right. So, only one direction. So, you will have neutrons coming in two opposite directions, all of them going in one particular direction. Now, this single layer can be replaced with multi-layer, and we can get multi-layer mirrors or super mirrors to get highly polarized neutron source. These are actually very important for carrying out magnetic structure determination. Having said that, another most important part of neutron diffraction is actually the detector. Most often, the most common detector is the helium ion detector, which comprises of a gas filled detector. We also use semiconductor detectors as well as scintillator detectors for analyzing neutrons. I have shown a few schematic of the cold neutron chopper spectrometer at Oak Ridge National Laboratory to just give you a feel for things. And here you can see that we have a Fermi chopper. Let us not talk about it, but it is like more of a chopper that controls the kind of wavelengths which are going in. We have a bandwidth chopper, then we have shielding. This is your nuclear guide, and here you see here is where our sample is, and these are all your detectors, right. So, these are pretty big, and you see this the entire source to sample, right. So, if this is your source over here to sample, this distance is huge, right, 36.2 meter, right, and everything, all of this is shielded, right, and all this you can see that why very high angles we can get information using the spallation source, right. Having talked so much about neutrons, let us now sum up with why at all neutrons are important, and for this we have to go to the energy momentum space diagram, and here we see that this is our energy and momentum diagram or reciprocal space and angular velocity diagram, right. And here we see that for different amount of q and our energy, this is, I mean, you can also plot it as your r versus t, right. R is the spatial distance and t is the time. We see that neutron scattering, you see there are various other techniques. We see Raman scattering over here, right. It is giving us some information about the time and the time related stuff and the distance related stuff about what is happening at a atomic level. So, you see Raman scattering gives us a very small information, which is even better than what we get in using NMR or certain other techniques like dielectric spectroscopy or infrared spectroscopy that is shown over here. But look at neutrons. You see neutrons gives us a lot of information. See inelastic neutron scattering, right, because of back scattering, right, gives us a lot of information. Similarly, here we have small angle neutron scattering and ultra small angle neutron scattering. So, we see when we compare at the q omega, right, the q omega plot for different materials, for the structure of different materials, we see that neutrons offer the ability to probe and cover the maximum region in the q omega space, and therefore, neutrons are very important source for carrying out material characterization. I hope you appreciate the importance of neutrons in materials characterization. In the next class, which is also the last class of this module, we will talk about small angle neutron scattering and wind it up. Thank you.